well, before talking about paired t-test, I'd like to talk about a little bit about the concept of noise in statistics. Now, basically, what we do in when we conduct a t-test, the t0 that we find is, you can look from this perspective. You can say that it's going to be the numerator of the t statistic value is going to be the difference of sample mean from the hypothesized population mean. This is going to correspond to what we call signal here. So this is the effect that we would like to determine. This is actually divided by standard deviation over square root of n. This is actually will correspond to what we call noise in our system. So what do I mean by that? Okay, in order to explain this, I'd like to go into philosophy, but just a little bit. Actually, for this part of the video may sound like a bonus video, but I'd like to keep it as a typical lecture video, because I'm not going to go into mathematics, and I think you need to understand those concepts so that we are going to be much more comfortable with paired t-test and with the concept of blocking here. So let's think about why do we have noise or variation in our system. One explanation maybe because actually think about, we have, let's say, a treatment, we apply it on different people, and we got actually x1, x2. These results are not equal to each other. Actually, we find the x bar value. Nevertheless, there is a standard deviation. Why do we have that standard deviation? One explanation maybe, and this is going to be from a deterministic perspective of the universe. It doesn't need to be that way. I don't say that I agree with the deterministic view of the universe, but just assume that it is, because it is easy to conceptualize noise here in this case. Then everything that happens with a cause, and that cause is specific to that. When that cause happens, the effect will necessarily happen. This is basically what the determinism is in a nutshell. And so every event has actually a cause, and one cause will not occur two different effects. So from this perspective, why do we have different answers although we apply the same cause, the same treatment to each of these people? The same treatment is given, but we have different outcomes here. This random variable takes different values. It's because it's not only the treatment, but there are also what we call nuisance factors. So each human, each subject carries those nuisance factors, factors that we cannot, that is independent of the treatment. On the other hand, that affects the result. So let's say this one is a little bit old, relatively old compared to these guys. So when this treatment is applied on that person, the change in X value will be treatment plus his or her age. And there's going to be a male-female difference between those two. And due to that sex difference, we are going to have a different treatment. We are going to have the same treatment, but the effect may be different, because also male-female issue is going to be also superimposed on that effect. So what I say is that all these differences between the subjects, between the specimen, will also have an effect, will actually have maybe a large or maybe a small contribution in the difference between those X values. So this is purely from a deterministic perspective. So every subtle or large difference in X values happens for a reason, happens due to a cause. And those causes, since we apply the same treatment, identical treatments, there may be very subtle differences in the procedure, of course, without realizing, or maybe we cannot control that much of the treatments, right? So you measure a certain medicine, a liquid substance, for instance, there may be very slight differences in the amount of the liquid injected to those different bodies. So there may be some variances due to those treatment, but there's going to be also variances in those specimens, and due to those variances, there's going to be difference. So here is the idea. Since T0 is actually a signal to noise ratio, that the differences between the subjects will increase the noise. How? Those differences will affect deviations of x1 values from the mean value or from one another. So therefore, S value will inflate. So what happens, what is going to happen when S value inflates or increases? Then noise will increase. And in this case, although numerator is, let's say it is constant, it shows the signal, it shows the effect of that treatment, the ratio is going to be smaller. So this is going to be a problem, because actually we compare this T0 value, whether that T0 value is greater than an upper control, upper critical value or not. But if this is greater than this upper critical value, then we are going to deem the treatment to be significantly effective, statistically significant, to be statistically significant, effective. On the other hand, this all depends in this denominator. When the noise is high, so when there is high variation between specimen, then it's going to be difficult to detect the signal. You may think about it in a way like this. Let's say you are trying to drive a ship, right? And let's say that this is the wheel of the ship, and the signal that I apply, the numerator is going to consist of this amount of wheel rotated, right? So in a very calm water, the amount or the how much I rotate this wheel is going to have a large effect here, because the difference, the standard deviation of the ship position, if everything is still, here is going to be very small. Therefore, the how much I rotate here will have a high effect on T0 value. But if there are huge waves around, right, how much I rotate will have a small effect on T0 value, because there's going to be a large standard deviation. And here standard deviation means corresponded to the identical condition. So the wheel is not rotated. How much variance am I going to have in the location of the ship? Since here there are waves, and this is my again ship, it may be here or here, even if I do not rotate this. So when I rotate this wheel, I would like a certain displacement to occur, but this displacement may be lost in this noise. So I think this is pretty much sufficient to explain the meaning of t-test, or the perspective, the interpretation of t-test as a signal to noise ratio concept. And here noise corresponds to, from a deterministic perspective, some nuisance factor on the specimen, which affects the result, which causes a change in the result. And if the nuisance factor have a large effect on the response variable, then it is difficult to determine the signal. This is what I would like to explain. So what can we do to decrease those nuisance factors, or to decrease the noise? Actually, one thing that we can do is in statistics, this is called blocking. Blocking in its definition, as its definition, it is to partition the subject into homogeneous groups. What do I mean by that? Again, let's think about different humans. Now, due to these differences in age, blood type, male, female, about weight index, other variables which may have potential effects on the response variable that we measure. The idea was, when we apply treatment 1 and treatment 2 on these people, that the result, the change or the difference in X cannot be only deemed to the treatments or due to the treatments, but these may be also caused, the change in X may also be caused by these nuisance factors. One thing that I may do is, if these nuisance factors are controllable, right? If I can detect those nuisance factors, and if I can control them, then I separate these people into homogeneous groups. For instance, what may be the nuisance factors? For instance, it may be sex, it may be age, it may be weight, or since I'm an actor, I don't know more about these stuff, but actually you can come up with, due to your previous research on that topic and experience, and due to other theoretical conditions, you may come up with some of these nuisance, controllable nuisance factors. So one thing you can do is, using those nuisance factors, you can form homogeneous groups. So what do I mean by that? There is actually an example I would like to show here from uh, a paper. All right. The paper is, let me try to show to you. All right. It is in Journal of Athletic Training Purpose, 2008, issues in outcomes research and overview of randomization techniques for clinical trials. For those who are interested, I recommend you to read it. It talks about randomization. I'll come to the concept of randomization in a minute. One thing that we can do is what we call stratified randomization here. And the idea is here, again, these male or female, underweight, normal, overweight, the whole population is divided into those groups. So each of these squares will correspond to a homogeneous group. Then when we have a control and a treatment or test that we would like to apply, or two different treatments, we actually apply these treatments to those people here. So in this case, four of these people will be, let's say, control groups, and three of the will form the control group, and three of the people here will be the test group. And when it comes to 5 here, it's going to be again divided by 2. If it's not divided by exactly 2, of course, you can, it's going to be an odd number. Then one of these is going to be larger. But this is instead of just lumping all of these people in a single, as a single object, and randomly taking people from those, this blocking perspective is a better idea. So why is that? Because within that group with male and underweight, note that the nuisance factors will be smaller. Therefore, noise will be smaller. What do I mean by noise? They are the effects which I do not want to include in my study. I would like to only include the control versus treatment effect into my study. So therefore, when by this way of blocking, I form a homogeneous group. Of course, there are going to be other differences, other things I haven't included here. For instance, maybe height may be important, or their diet, it may be important. How they eat, how they sleep, or how, whether they exercise or not. So there may be many different variables, but considering at least the most important variables which may have an effect on the result, you may block these and come up with such a system. And for those systems, again, for instance, we have 7 people here. Now, when we have to choose half of them from the control, half of them for the treatment. For this case, although we know that this is not a purely homogeneous group, there are still going to be some heterogeneous elements, as I said, for instance, blood type or other elements. So in order to overcome those nuisance factors that we cannot control, what we do is randomization. So we randomly assign those 7 people to control and treatment groups. So to sum it up, when you have controllable nuisance factors, you do blocking to form homogeneous groups. And once you form homogeneous groups, you have to still realize that there may be uncontrollable nuisance factors, and to get rid of them, what you do is randomization. So this may be a better strategy compared to total randomization of the whole group by this way, because within each of these cells of homogeneous subjects, we are going to be decreasing the standard error or standard deviation or variation here. So basically, within those groups, at least theoretically, if we do not think about the uncontrollable nuisance factor, we are going to be solely concentrating on the effect of treatment here, with no observable or controllable nuisance factors. Well, I don't want to go into this paper. Actually, it's a very interesting paper, but maybe as a bonus lecture, I could have done that. But I think it's better that for those who are interested, if you read this, it's going to be, as I said, interesting. And now, there is another thing which I would like to mention. It's like a side note. Still, I'd like to mention that. And randomization is not that much straightforward. Even I would like to talk about that. So, what do I mean by that? Because how are we going to perform a randomization? Let's say we have 10 people and we are going to select a control and a treatment group. And the most common way of doing is flipping a coin. So for the first person, you flip a coin and let's say he or she comes out to be control and you do the same thing. But note that when you have a small sample size, a small number of specimen or subject, then it's going to be pretty much possible or probable that you are going to obtain unbalanced control and treatment, the number of control and treatment objects here. So it's not going to be with a high probability. Actually, you can calculate it using binomial distribution. 5 to 5 partitioning is only a single value, which is going to be compared to other partitions. It's going to have a lower probability. So it's even the simple randomization, the procedure itself is not that much straightforward. Actually, it's explained in this paper how, for instance, the called block randomization is conducted to overcome that issue. Okay, I think that's uh, enough with those subjects. Let me come here again. So basically, blocking is, as I said, partitioning data or partitioning subjects into relatively homogeneous groups. Now, paired t-test or pairing is the simplest blocking, I may say. Here in pairing, our groups, our homogeneous groups, is formed by each individual or each subject. So if we have 6 subjects, and if we are going to, for instance, test treatment 1 and treatment 2 here, we are going to apply treatment 1 and treatment 2 here. We are not going to apply half of them with treatment 1 and half of them with treatment 2 as in independent t-test approach when it comes to pairing procedure. What we do is we take each subject and we apply treatment 1 and treatment 2 on the same subject. And we do this for all the specimen or all the subjects here. So basically in this concept, what we do is each subject forms its own group. You may look from this perspective. So it's like we have one female, we have one male, and these, let's say, old and relatively older female, relatively older male, a young male, a young female, and a child. Okay, you can think about any other. So a very heterogeneous group. So actually here blocking may not be in terms of groups containing more than one person may not be a very good idea. So the simplest thing is that you apply both treatments on the same specimen. Unfortunately, for instance, if we are talking about, let's say, we have a lubricant or we have 2 lubricants, lubricant A and lubricant V, and we would like to test their polishing quality. And we have some metal pieces here in a bag. And in independent t-test approach, what we do is we take half of these metal pieces and use lubricant A on it, and half of them use lubricant B on that, and see how the difference, if there is a difference or not. But in paired t-test approach or in pairing approach, pairing the lubricants approach, what you do is we take each subject. Let's say this is a metal object, and half of this is going to be the lubricant A is going to be applied on this half, and lubricant B is going to be applied on this half. This is actually very similar to those commercials, right? Actually, we have a shirt here. It is dirty, all the stains around. So half of this shirt is washed with a certain detergent A, and half of the other half of the shirt is cleaned with detergent B. And then they check the difference between 2 sides. That is exactly a pairing procedure, a paired t-test approach. It's not we take one shirt here and we washed it with detergent A, another one we washed it by detergent B. Actually, in this case, the result will not only depend on the quality of the detergent, but also the dirtiness of the subject as a cause on the result, which is going to be the final cleaning amount, I may say, is going to highly depend on the state of the shirt. So therefore, to block that effect, which is the variation due to the differences about the initial cleanness of these shirts, if there is such a way of expressing this phrase, then what we do is we take a single shirt and we apply half of detergent A, half of detergent B, and we apply it for other shirts. So this is similar case about these lubricants. So you take each of these metal pieces, half of this piece, half of this piece. But there is still an issue here, and there is still some randomization to be employed. For instance, when it comes to shirt example, whether it's going to be right hand side and the left hand side is going to be used by detergent A and B. You may say, what's the big deal here? Here is a story. If let's say we are talking about a footballer, right? He plays on the right side of the field or left side of the field. It may be such that his right or left side is likely to be more more stained. This may be the case, or maybe it's not the case, but this may be there may be such a causal relationship, which is going to have a unsymmetric effect of being there's going to be whether the right or the left hand side is going to have more stains. Therefore, since we have now in this case a single shirt is not of course sufficient, we are going to have all these different shirts. But when it comes to each shirt, the left hand side or the right hand side is going to be cleaned with detergent A. It should be decided by a flip of the coin, right? So for this shirt, a coin is flipped and the left hand side is going to be detergent A. For this one, left hand side A. For this one, left hand side A. Right hand side A. Okay, so it goes like this. So randomization still need to be applied here, same as lubricant example. Okay, but on the other hand, when it comes to humans, that's not that much straightforward with the treatments, because when you have a human, you cannot apply the right hand side and left hand side with a certain treatment. If we are talking about a pill, for instance, if we are talking about, for instance, an exercising machine, you may use, for instance, your right leg and left leg. Still, you have to use a randomization. This is, by the way, supposed to be a person, and this is the two different exercises for the right, for the left leg and for the right leg. Still, you need to apply randomization, because the strength of leg, right and leg, right and left legs need not be identical, and this may affect the results. Anyway, but if you are going to use a pill, for instance, for a certain disease, it's not very straightforward to use pill A, for instance, then use pill B, because there may be some residual effects of A once you use it, which is going to change the effects of B. So the effect that you think that is due to B may be the effects of B plus residual effects of A. Furthermore, there may be some interaction effects here. When you use pill A and then you use pill B, there's going to be an unwanted side reaction. Maybe B is a very good pill if you take on its own, but after you take after A, it's going to cause a problem. So the time ordering here should be such that this effect of A and effect of B should be independent, but there are other, actually there are whether that independence can be employed or can be realized in an organism is also questionable. So so you may think about a vaccine. When you apply a vaccine here, now the human organism adapts itself to a vaccine. So however long you wait for if let's say a month, 1 year, still it's going to be effective when you apply B, which may be related or which may interact with that vaccine. So this is itself a not easy topic, but we are going to not going to go into those details. Anyway, so that was the introduction related with the meaning of blocking, and also pairing treatments on single observations. So now this is how we and why we conduct pair t-test. Now, the arithmetics here is going to be very easy. Now, note that the important point, when we apply the two treatments on the same specimen, now if there are pretty much wide changes between specimen particle, if they form a heterogeneous group, and these other properties of the specimen, whether they are controlled or uncontrollable or uncontrollable nuisance effects, if they have large effect sizes, then we can easily see that, for instance, let's say this is a slightly heavyweight guy, and this is, or not, let's not talk about people, let's talk about again that polishing thing, or polishing, yeah, polishing thing. Let's say this is a material which is very easy to polish. So in this case, when you divide it into half and when you use treatment A for lubricant A and lubricant B, the result is going to be nice or acceptable for both of the surfaces. But let's say this is a very old metal piece, so it's very difficult to polish. So when you apply treatment A and B, the result is not going to be bright for both sizes. So what I would like to say is that if the heterogeneity between specimen is high, and this heterogeneity has a high effect on the random variable that we measure, then there is going to be a very high correlation between those two treatments. So if you write here treatment 1 and treatment 2 for different specimen, the effect of treatment or the result of your measurings is going to be here. Whether treatment 1 is better than treatment 2 is another story, but there's going to be a very high correlation between those two. It's going to be most likely greater than 0. It's going to be maybe close, not maybe close to 1, but it's going to be a high correlation between treatment 1 and treatment 2. In this case, and as you can see, this one is better, this one is better. This one seems to be bad, this one seems to be bad. That is the correlation. So in this case, we cannot apply independent t-test, because in independent t-test, our assumption is this x1 bar is independent from x2 bar. And this independence assumption is violated here. So therefore, we are not going to take each side's sample mean as x1 bar and x2 bar and find sample standard deviation S1 and S2, then do the computations. That's not what we are going to do, because we violate the independence assumption. What we do is we need to determine independent statistics, and that independent statistic is going to be the difference between those two sides. We are going to define x1 and x2, and difference between those two is going to be D here. For instance, for the first object, for the first specimen, D1 is going to be equal to x1 1 minus x2 1. So for the first item, the first treatment result, for the first item, the second treatment result, the difference between those two. So in this case, D bar is going to be the statistic that we are going to use, and D bar is going to be equal to x1 bar minus x2 bar. Well, actually, you can easily show that this is the case, since this is how D is defined. Actually, D bar is equal to the I values from I1 to N divided by N. Therefore, this is going to be equal to xi I1 to N x1i and x2i and from I1 to N, and this is going to be equal to x2 bar, and this is going to be equal to x1 bar. Okay, so and the expected value of D is going to be, of course, equal to expected value here of x1 bar minus x2, and this is going to be mu1 minus mu2, which is going to be equal to mu D. So hopefully now we have a nice statistic with that expected value. So we are going to have a D bar here. Is it going to be normal distributed? Yes, because x1 and x2 are assumed to be normal distributed. Therefore, their linear combination, which is here a subtraction operation, is going to be linear distributed. There is one thing here which is left. Well, this normal distributed, the expected value. What about the variance of D bar? Now, D is here. We are interested in variance of D. actually variance of, let's put it that way, this is going to be equal to variance of D divided by N. So what we need to find is this quantity, variance of D. What is that equal to? So actually this is equal to variance of x1 minus x2. And this is going to be equal to variance of x1 plus variance of x2. Is that all? No, this is the important thing. We are also going to have minus 2 times covariance x1, x2 term. Because if it were only those two terms, actually that variance of D would be greater than variance of x1 and variance of x2. So that would be that would oppose to our purpose, because our purpose is, as I said at the very beginning, to decrease, if you again remember the t-test here, we would like to decrease this standard deviation. We would like to eliminate the contribution of nuisance factors to those standard deviation, because when it goes down, the numerator is like the effect of the numerator will be more clearly seen, because t0 value is going to increase. So this part is related with, actually is exactly equal to this term here. It's going to be standard deviation of D square root of N. And standard deviation of D should be a smaller number. And note that it is this part which is going to make this value smaller, because these are variance of x1 and x2. They are added together, but we have also two covariance x1, x2. In other words, it's going to be 2 times sigma x1, x2 sigma x1 sigma x2, because if you recall, it's going to be equal to covariance of x1 x2 divided by sigma x, I'm sorry, sigma x1 sigma x2. So instead of covariance, when you write this is going to be more obvious. Now these are positive numbers, as I said, for most of the cases, right? So if this specimen, due to its property, if the specimen, the properties, the inherent properties of that specimen, that nuisance factors is like to have the same contribution to both treatments, right? So in this case, there's going to be, as I shown here in this part of the presentation area, there's going to be a positive correlation between those two, which is going to decrease this variance. Variance x1 minus x2 is going to be smaller than the summation of these two values. And this is going to make the variance of the smaller. This is going to make this denominator smaller, hopefully. So can we predict this? Unfortunately, no. Without applying these two treatments on that specimen and measuring the effects, we would not be able to determine this value. And since we actually, instead of going on all these calculations, we don't need to do that. What we only need to do is to compute or to come up with an estimation of this value. And the best way of the estimating this value is actually, once we have the D values here, right? So they are going to have a D1. We are going to have, these are numerical values. That's why I write in lowercase letters, Dn. We find the average D value here. And we are also going to find standard deviation of D values here. Then when you divide it by square root of N, or it's going to be sample variance, N is going to be an unbiased estimate of D here. So once we calculate this, we are going to have obtained this. So what we do is we are just going to use now the t-test on this system. Once we design and construct and execute the experiment in pairwise manner, and since we have already defined D as the difference between those two treatments, the observations obtained from both treatments on the same specimen or on different parts of the same specimen, the hypothesis test would be constructed on D alone. So the expected value of D is going to be hypothesized to be equal to a D0 or delta 0 value, versus this not going to be equal to D0 value. Note that this is a two-sided hypothesis test. Of course, we can write one-sided version of this one. Our test statistic is going to be equal to our computed sample mean of D minus D0 value here, or delta 0, divided by standard deviation estimate of d bar, which I talked about, which is going to be equal to SD. This is going to be computed from the difference of those two treatments. They are not going to be computed from the individual standard deviations of these two treatments. They are going to be determined from d values divided by square root of 1. And here there's going to be also the corresponding confidence interval. One does not need to, I think, explain anything about this because it's very similar to what we have covered here. The only thing is that we have the central point here, d bar. The same quantity is subtracted and added, and that quantity depends on a t value. T distribution will be with n minus 1 degrees of freedom and the standard error term here. So let me try to solve a simple question. We have two different formulations which corresponds to two different treatments to produce a chemical, and we are interested in the final concentration. So we are going to see whether these formulation yields identical or different concentrations. So note that these treatments should be, or the formulation should be used by chemists to produce that specific chemical. So we have 9 chemists total here. Well, instead of dividing them 5 by 4 and assigning one formulation to those 5 group and the other 2, we let these 9 chemists, each of them, apply both of these formulations and produce that chemical by these 2 methods. And using the one from this perspective, it's going to be a paired t-test. So we obtain the data, but before obtaining the data, let's define the question. So D is going to be defined as the difference in concentration concentration of product manufactured by formulation 1 and 2. Difference in the concentrations of the products, that is better, I think, manufactured by formulation 1 and 2. And the hypothesis test that we would like to be conducted is going to be mu D is equal to 0 versus mu D is not equal to 0. Note that now I write this in terms of D, not x1 and x2, because I'm going to be interested only in the difference. So note that this last statement can easily be changed into these different forms. Actually, you can say that this is also can be written this equivalently. It can be written as mu x1 or mu1 is equal to mu2. These are actually two equivalent representations. On the other hand, usually we reserve this representation for independent t-test where we use mu d is equal to 0 for the paired t-test, so that we can realize or remember that we always work on the difference between the between x1 and x2. And we are going to conduct this test, let's say 0.05. Our test statistic is going to be equal to d bar value minus 0, because this is the hypothesized value in null hypothesis, divided by SD bar, which is going to be actually SD over square root of n. So actually we are going to be doing all the computations on the sample mean is going to be computed from the difference values. Sample standard deviation is going to be computed from the difference values. And we are going to check this. This is going to be if the null hypothesis is true, assuming that this A0 is true, this is going to be distributed with n minus 1 degrees of freedom if H0 is true. So hence we find T alpha over 2 and n minus 1 value to check the upper control upper critical value. So this is going to be T 0. Let's take this 0.05. This is going to be 0.025 with how many experiments did we perform? Actually, I still haven't shown you the experiments, but they are going to be actually 8 experiments. I'm sorry, 9 experiments performed here. So it's going to be 8 here. So you can look from your textbook. I think this value is something like 3.300, something like that, if I recall correctly. So we are going to calculate T0 and check whether this is greater than this limiting value or not. So we have conducted the experiment in this fashion. Let me erase this part so that we can see this part more clearly. All right. These are the experimental results. So chemist one has conducted an experiment on formulation one, and this is the concentration he come up with. And using formulation two, this is the result that you come up with. Now note that when you design this experiment, you have to randomize the order of these two formulations. Why, you may say? Well, there are different reasons. For instance, I may come up with a pretty much plausible causal relation in which when the chemist, any chemist is experienced in any of those formulations, he or she will be more proficient in applying the second formulation. So the second result is going to be more reliable, or the concentration will be higher if higher concentration is something to be desired in the second formulation, I may say. Or another causal relation may be related with psychology. Let's say that these formulations are so difficult and these chemists are so underpaid that during those experiments, once he or she, any chemist is through with formulation, any formulation, then he or she would be too much bored to apply another, but again similar for the formulation for a second time. So she or he wouldn't care as much as the first experiment that she has conducted. So this result will be less reliable, or the concentration will be lower than it should be. So, or other factors may be in action, I may say, but this most of this may be related, or some of this these effects may be related, as I mentioned, related with psychology, and maybe there are not such effects. But on the other hand, the order of the experiments may have a nuisance factor, a factor, an effect which may cause a change in the results. So therefore, we should randomize this effect. So these orders are randomized, and these are the results that we have found out. Now, the important point is when you conduct a paired t-test, and you should understand from the story here, not this how this data is listed. Note that I could have easily listed data as chemist. Well, okay, here is how I could have listed this data so that you might have been you might have thought that this is an independent t-test, and this is let's say concentration value. Okay, chemist 1, formulation 1, concentration is equal to 1.186. Chemist 1, formulation 2, 1.061. Chemist 2, formulation 1, 1.151. Chemist 2, formulation 2, 0.992. So this actually would have been composed of 18 rows. What I would like to say, that do not be just fooled by thinking that just looking at this table, oh, okay, this has two columns here, so and a single subject here in each row, so this should be a paired t-test. I can very easily change this table into a form which might at first instance look like an independent t-test formulation, but actually you should understand from the story here, from the how the experiment is conducted. By visualizing this, you should have concluded that, or you should conclude that this is a paired t-test experiment. Anyway, so what we do is we do not work with these values, each of these x values here, the very important thing. We do not find x1 bar, we do not find x2 bar. More importantly, we do not find s1 and s2 here. What we do is we find the difference between all these values, x1, x2, this is equal to that one. So these are now our independent samples. Note that here each d value will be independent from the other one. That's how we can justify using the t distribution. Each observation of d is independent. Well, two different formulations, okay, but the difference between them, I don't need to repeat again, is independent from the other values. So in this case, we come up with d bar and st values here. And when you do that, actually the whole table is like the other questions, they are not complete. I just skipped that part. So d bar value is going to be found as this value, and st is found to be equal to this one. Let me again get rid of all these messy parts. All right, this is, I think, better. So now we can finish the question. T0 value is going to be D bar, which is 269, divided by this SD value, divided by square root of 9. And when you compute this value, I have to check from my notes, this is equal to 6.15. Now note that 6.15 is larger than our upper critical value. Therefore, formulations do not yield identical concentrations. This is our result of our hypothesis test. Let's also find the corresponding p-value for this test so that we are going to have a better understanding about the this reliability of this result. So to do that, actually, we try to encompass the T0 value at 8 degrees of freedom. Actually, the lowest T0, I'm sorry, the highest T value with 8 degrees of freedom that you can see from your table is this value, 0.0005 with 8 degrees of freedom is 5.041. And since our T0 value is greater than this value, therefore our P value over 2, remember why we have over 2 here, is going to be smaller than 0.0005. What number of zeros? Okay, 1, 2, 3, 1, 2, 3. Yes. So P value is going to be smaller than 0.001. So our P value is going to be smaller than 1 in a 1000, which shows that this result seems to be pretty much reliable. I repeat, you couldn't have solved this question using the independent t-test procedure because these two observations are not independent.